Cool, let's go for it started. Okay, if we've got time, I will answer and go through all of the stuff that you guys want me to do. Cool. So what are we actually gonna cover? I'm gonna talk about, we'll start from basics. I also teach through exam questions. So if you look through the slides, I will send you guys after the session. It's all exam questions. So I'll be teaching you guys through them because I think it's the only interesting way to do it. So there's OCR and AQA questions, but they very much align with what you both need to know. So we're going to talk about how to name them, how to actually make them, because there's two ways how to prepare them, the basicity of the properties that you need to know probably come up this year, nucleophilic addition and elimination, amino acids if we have time. We'll talk a bit about amides. Chirality is a given with amino acids, and I want to talk to you about phenylamines. All good with that? So there's a lot to go through. But we'll get like a whole idea of everything that you need to know. So I'll ask you guys questions because obviously we're only 3 days away from the exam. So there's 3 types of amines that you can get. You can get primary, secondary, or tertiary. You need to know how to name them. So with primary, I think everyone's okay with naming them. I think what they find difficult is when to deal with the capital N. So when does it become N substituted? So my little rule of thumb typically is a typical amine molecule is NH2, right? So you have NH and then N. That's the different properties that it can come up as. This is typically primary, this is typically secondary, and this is typically tertiary. For every H that you remove, you substitute an N in. That's typically how it works. So because no H's have been removed in this case, we don't have to N substitute. In this case, there has been one H, so we do one N. And then if you have 2 tertiary, 2 H's have been removed, so you do NN. Does that kind of make sense? So I would say have that on a flashcard if you struggle to name them. So with the first one, we've got CH3NH2. So off the bat, you need to decipher whether it's primary or secondary tertiary. Obviously in this case, because it's NH2, we've got 2 H's, it is primary. So then you look to the side of it and see what is attached. So we can see a methyl group. So here I will say methylamine. Okay, so this one will be methylamine. So the next one, if we look here, everyone happy with the fact that it's secondary because you've got 1 H and not 2 this time, yeah? So you need to look at, the N is there to basically justify what is it actually attached to. So you need to go to the closest side chain. So in this case, the closest thing and the smallest chain attached to the amine is a methyl group. So because we know it's secondary, I'm going to get my N out the way, and then I'm going to get actually the smallest thing that it's attached to. So in this case, it's a methyl group. So then on the other side, can anyone finish what the name would be? So it's N-methyl what? Just put it in the chat. Okay, so we're getting ethanamide. Ethyl, yeah, so ethanamine. A lot of you get confused between an amine and amide, okay? I'm going to just nip this in the bud now. Amines and amides are 2 different things. An amide is like an amide linkage, so it will have to be an NH attached to a C double bond O, okay? That is an amide group. They will throw you off sometimes in questions where they'll have a whole compound with like a NH2 like this, and then you have a double bond on that side. They have to be directly attached for it to be an amide linkage. So in this case, we wouldn't call it an amide. You would name it normally, like in this case, the carbonyl group may take priority, for example, and then you go with like amino whatever. So be careful with that. So an amide is when they're directly attached and you have an amide linkage. In this case, it's not amine because there's no double bond O. Everyone happy with that? We'll do some practice questions when we get to that. Then with this one, you've got a tertiary amine because you've only got 1 N. So again, you need to look at what is the simplest way to deal with it. Because it's tertiary, I know that I'm going to have NN out the way. So then you need to read like the easiest side chain. Here is the easiest side chain because it's a methyl group. So I will go with dimethyl ethanamine. So those are the like basic rules in terms of like naming. Deciphering if it's an amine, decipher if it's an amide, if it's tertiary, secondary, or what, put your ends in, and then that's the easiest way. Cool. So let's do some questions. So I want you to have a look at this. Which one is the secondary amine? So you're definitely going to get asked this. Just put A, B, C in the chat and we can go through it. Perfect. Good. A. So obviously these lot have got like one, like it's just a normal N. So we will say these are tertiary. So then you think these are secondary. The one that throws people off is this. The reason why, well, what is that? Can anyone say what that is? An amide, exactly. It's got that amide linkage. So it's like what I said to you, they like to throw you off by putting an amide in there, but this is an amine because it's not attached to that double bond O. Okay, so let's do another one. Have a look at this one for me. Cool, we're getting a mixed bag. We're getting A's and C's. Okay, so it's asked for an amide. So you need to, and a secondary amide. So I would go through the list and get rid of your tertiary ones first. So this is tertiary because you've got loads of branch molecules, and this is tertiary. So I'd get rid of B and D. So you're left with A and C because they're secondary, right? Because you've got that one H attached. Now it's asking for amide. So I would go for C because you've got that amide linkage there. Whereas here it's an amine because your double bond group is all the way over there. Everyone happy with that? That's kind of it on naming and classifying, okay? Especially if you're OCR, you will probably get an MCQ on it. They like it. Cool. Cool. Right. Now, next things we need to talk about is branching and basicity. Okay, so basicity we'll talk about, but they liked this question a lot where they talk about branching, so it's going to be quite easy. I want you guys to talk to me about, so you've got a carboxylic acid group. Can you see this here? So it takes priority. Okay, so that's when you would think to put amino and then give the carboxylic acid group priority in this case. So read them out, read the carbon chain and go from there. Does that sort of make sense? So that's what I was trying to say to you. That's when amino comes in and the carboxylic acid group takes priority. So generally, carbonyls are preferred and they like to take the end, like the suffix, that's what you call it. Everything else typically takes a prefix. Cool. Okay, obviously I'm going to quickly go through the branching of it. So can everyone talk to me about like the order of branching? So we've got different types of like, well, what sort of amine is that? Primary, secondary, tertiary? Exactly, tertiary. Cool. So what it doesn't have what bonding compared to the other ones? Exactly. So you've got that one, which has like no hydrogen bonding in comparison to the other ones that do have hydrogen bonding. So we also need to talk about chain length as well. So you've got one here, which has got really, really long chains. And then that you go back to AS and you think, well, longer chain, more surface contact points. And then you need to talk about hydrogen bonding. So then you then order them based on that fact. Cool? I'm not going to spend too much time on that one. I think everyone's happy with that. Cool? Everyone happy? Cool. Right, so let's talk about basicity. I think AQA is probably going to get this year. Even OCR, actually, it's Freeway. Yeah, I'll bullet point it for you. So I would say, I'm just going to name it 1, 2, and 3 because it's going to take me ages to do it, okay? So 1 has the longest chain, more surface contact points. And then you can say 1 plus 2 have hydrogen bonding. Other things that they would probably want you to say is that this one you can probably even say either or, no hydrogen bonding. What other bondings are involved? You've got hydrogen bonding, but what other forces would you talk about? So van der Waals, London forces is fine. Okay, so you could say the other one has, you could say H2 bonds. I'm just going to put increase higher than London forces. You can have, that's fine. And then obviously your last point is obviously, therefore, it takes more energy to overcome. Both, this is an, AQA has to know about this as well. So both of the exam boards need to know about this. Even like, they don't really like to ask it about amines. They could ask it about anything. They could give you like normal side chains. You need to both know it about like long chain surface contact points, high melting point, whatever. Cool. That's it, basically bullet pointed for all the marks. Right, let's talk about basicity. So does anyone know what the basicity of amines is based on? What do we focus on? Exactly. So it's all about, when you think about basicity, I want you guys to all think about lone pair availability. Okay. Now this is quite good. I will kind of reference phenol as well, because phenol kind of has a similar, its acidity, but I will talk to you about how it can relate to phenol in a similar like sort of explanation. So they're going to ask you to name it. I'm going to start off with this one. So what do we normally name E? What would we normally call E? Right, we've got a few. So you need to name it phenylamine. Now, a lot of students get confused, like, why is it phenol? Typically, when you replace one of the H's of a benzene, it goes into a phenol. Okay, if it's not like a methyl group or anything, typically it's a phenol, sorry. So that's why it's phenylamine. Okay, so the issue with phenylamine, is it the most basic one or the least? Okay, so the reason why it's the least is this. It's all about lone pair availability. If you have an NH2, right, your nitrogen has a lone pair on it. Now, the the ring in the benzene group, is it full of electrons or is it electron dense? Yes or no? Yeah, that's why it's susceptible to electrophilic attack, isn't it? So what happens is the lone pair from the amine gets so used to having something that is so electron dense that it will donate its lone pair to the system. And that's why the lone pair is no longer available. So that's why it's the least basic, because it's the lone pair basically becomes unavailable. It would rather go to the ring than actually perform a base reaction. Is everyone happy with that? Now, the reason why, I don't want to confuse you guys, but obviously you've come here just about amines, but I think it's all about collaborative learning. If we have phenol, right? It's the similar reasoning for phenol. They like to ask you, why is phenol more reactive than benzene a lot of the time in your exam? Same sort of reasoning. The reason why is your lone pair from your OH on your phenol will donate to the system, which means this is more electron dense and then therefore more susceptible for electrophilic attack. That's why it's more reactive than a normal benzene. Is everyone happy with that? You will probably get asked that as well. And there's no lone pair available this week. Exactly. Okay, so I will explain that again. So the question is, they could ask you, why is phenol more reactive than benzene? Okay, the reason, do you want me to bullet point it out for you, like what you would say? Yeah? Okay, I know this is not relevant to amines, but you might as well. So the OH has a lone pair. Donates it to the pi ring system. You can also say the lone pair becomes delocalized as well. So that will also give you a point. And then I'll carry on here. More E minus, electrons in the pi ring system equals more susceptible to electrophilic attack. Is that okay for everyone? Yeah. So that's what you'd say for a 3-marker. What's the difference between N electrons going in? So the O electrons, so with phenol, they ask you about reactivity. With the N, I'll bullet point the answer here. So you could say they've got delocalized electrons. So the lone pair on the NH2 delocalizes. It donates it to the pi ring system. So the lone pair is less available. Because remember, if it's a base, is it a proton donator or a proton acceptor? If it's a base. Okay. Right. So it needs a lone pair. It needs to take in the H plus, right? So if it doesn't have the lone pair, it can't act as a base to do that. Equals less basic. So that's basically what you need to basically say if they ask you a separate question. Is everyone happy with the bullet points that I've made so far and what you need to say? This is the weakest. So let's talk about the other ones. Now, the next thing, someone put it in the chat, it's about positive inductive effect. Okay. So out of the two with G and F, which one is more likely to act as a base? Which one's easier to attack? F or G? Which amine? Perfect, because it can go straight here and do it, whereas otherwise it's got this bulky chain across it. So that's why you end up having the order as E to G to F. Now, the reason is that you can say it has a higher likelihood of positive inductive effect because it's easier for the reaction to occur. So you could say the lone pair is more available to donate or accept a H plus. So it's lone pair more available to accept a H plus. So do you see how it's more available than that one? That's why you'd say F. Everyone happy with that? So that covers all aspects of basicity and why. I thought the question before was why phenylamine was less reactive than benzene with alcohol group though, but they do the same thing. So the reasoning, I'm sorry I brought in phenol. I thought it would be helpful for you guys because we could cover more. But phenol, they'll ask about reactivity. But do you know how the reason why I brought it involved is the whole point is they both donate, like their electrons delocalize and add to the system, but the reasoning for the questions they'll ask you in the exam is different. So think for phenol, when it donates, think about reactivity, and then think about NH2, think about it delocalizes and adds it, that makes it less of a base. Is that okay, Ellie? Cool. Everyone happy? Any more questions? I'm going to move on, yeah? Cool. Right. Let's do some synthesis. So we've done naming, we've done basically how the basicity and all the wordy questions. I'm going to sit with you and do some synthetic routes and mechanisms, okay? So there's two ways to basically make an amine, right? So can anyone name me, anyone put in the ways that you know how to make an amine? How do you prepare an amine? Okay. So yeah, everyone knows you can do reduction of a nitrile. And then you got haloalkane with NH3 and ethanol. This is so important. These are the backbone of amines. So you need to get these written down, okay? Now, I also want to highlight, a lot of you don't know the difference of when they say to you, name the reaction and then name the mechanism. Okay, because a lot of you, for example, will say, oh, the reaction is like reduction. That is right. So when they say name the reaction, that's when you start naming it like it's reduction or it's oxidation. But if they say name the mechanism, make sure to say, oh, it's nucleophilic or electrophilic. That's the difference between those two questions. So please remember the wording. Okay, so let's talk about synthesis. So we've got methylbenzene, and they want a 3-step synthesis. So we need to talk about how we would get to an amine from methylbenzene. So I always say it's a bit tricky, but if you keep this as a backbone, that is fine. With a haloalkane, can I get to a nitrile? How do I get to a nitrile from a haloalkane? What's your reagents? There we go. So you can have KCN with ethanol. So that's how you go from like your haloalkane to a nitrile. Okay, so the reason why I'm asking that is step 1, you could go from a methylbenzene to a haloalkane. You can go to a nitrile for synthesis step 2, and then you can reduce it to an amine for 3. Does that sort of make sense? How you would do that for your 3-step? Okay, do you have any good ways? To be honest, a lot of them, I think it's worth learning the synthetic route, but sometimes it can get confusing because it's like so many lines all over the place. So I would go through each of the compounds and just bullet point all the mechanisms you need to know, and then just get flashcards off it. So I would probably say memorize it that way if you are struggling to see it all as a bigger picture. Okay, so let's actually write down how we would do it, because they want their reactions and reagents and all sorts. So we're going to go from methylbenzene to a haloalkane. Does anyone know how we would do that? So how do you go from like a normal bog standard hydrocarbon to a haloalkane? It's one of the first things you learn. Got a few. We've got the right answers in the chat. Yeah, free radical substitution. So you got to think, the benzene, you need to think about it separately. Your methyl group is where you're going to want to add your amine, okay? So your methylbenzene is useless. It's a normal hydrocarbon. It's unreactive. So you have to go back to basics and think, how do we make alkanes reactive? We do free radical substitution and make it an alkane, a haloalkane. So for step 1, methylbenzene, 2, we want to get it to a haloalkane. So we do UV light plus Cl2, and then you end up getting C6H5, because that's your benzene. Remember, one of the H's get replaced with the CH3, and then we're going to change it to that. So is everyone happy how I got that? Because this is C6H5CH3. So one of the H's gets replaced by Cl, yeah? And we're using I'm just using chlorine because it's like easier, but you could use bromine, I guess. Right, step 2, we're going from C6H5 CHCl, and I want to get it to a nitrile, so we're going to do KCN and ethanol, right? So the Cl is a good leaving group. So whenever you see chlorine, it's absolutely useless at committing to anything. The reason why they like to put chlorines in things is because it just leaves. So that's why you see, like, that's why we use acyl chloride based mechanisms, because they will just leave and then get replaced. So that's why, that's how I remember, in the fact that when you're actually making a product, you'll just have the Cl move and it will make a CN. You can use any acid. I just think about, like, I would just think any aqueous sort of alcohol sort of thing is fine. But I just remember KCN or ethanol, or you can have HCN, because you need the H plus. That's what you need. Cool. Next thing we need to do is C6H5 CH2CN. How do we do reduction of a nitrile? There's 2 ways. What's the 2 ways? Perfect. Yeah, good. So the exam appropriate way is H2 and a nickel catalyst, right? But it is reduction, so you can use a reducing agent. In the allow section, it will have lithium aluminium hydride. Okay, so that will be in the allow section, and that's how I would synthesize this question. Everyone happy with that and how I did that? Thumbs up, thumbs down, let me know. Cool. Right, let's go on to the next one. So primary amines can be prepared by the reaction of haloalkanes with ammonia or by reduction of nitriles. Justify the statement that it's better to prepare primary amines from nitriles rather than haloalkanes. What would you write for the product? Oh, so you would just do C6H5CH. We replace it. So what do they want us? They don't want the product. Let me double check. They don't want the. A lot of the time with mechanisms, you don't have to write it. So you're just fine, like you're just gonna make like NH2. That's basically what you're gonna have. Cool. Right. With this one, why do we not like halogens? What's the issue with halogens? It says to give the two intermediate compounds, which we've gave this one and this one. Yeah? Don't worry, don't overwork yourself. So we've got, yeah, so someone said it. The reason why we don't like haloalkanes is because they do further substitution. So in this like question, just say like, well, we don't haloalkanes do further substitution, or they form impurities, whereas nitriles, they have a high atom economy, they don't have any of those further reactions. So that would be your 2 marks. That one's done. Okay, let's talk about this one. So we're make amides, and then we need to know how to name them. So I'm going to quickly do that with you. So with this, a lot of students get confused how to kind of deal with naming the mechanisms. The other one is just further substitution for a haloalkane or more impurities, or you can say low atom economy. And then they want you to say something about nitriles, so just say the opposite. High atom economy, less impurities, no further substitution, okay? That's it. I'll give you a sec. Cool. Right. So my typical way of remembering this is anything you did in AS. What's the first name of the mechanism you ever learned in AS? Obviously not free radical, but what's the first one you ever did? Some of you got taught nucleophilic substitution, yeah? So nucleophilic, what's the other one? I think OCR, you get taught another one first. Elimination, electrophilic addition, that's what I was looking for. So these are the 2 ones that you learn in AS, right? So I always think these are the typical ones that we see with alcohols, alkenes, like alkanes, whatever. Those are the ones that you need to associate with. Now, second in A level, you learn electrophilic substitution, which is with what compound? What's the only compound that can do electrophilic substitution? Exactly. So benzene. And then what do you have here? Nucleophilic addition. So you have your harder compounds that no one likes, which then is like your acyl chlorides and like typically your carbonyls. Okay, so that's how I kind of remember in your head about how to remember what the name of each of these mechanisms are. So this one's asking you about acyl chloride. So what is it likely going to be? What's the name of the mechanism? Yeah, nucleophilic addition elimination, technically. Yeah. So try and associate compounds with how you learnt them. If you forget the name of them, typically that's how I remember. Let's do this. So this one, I feel like you'll probably get asked. Either or of you could get asked this because they like to ask an acyl chloride mechanism a lot of the time. So let's do it. So we've got your double bond O, you've got your Cl, you've got your CH3, and then your CH2. Okay, Cl, remember, is useless. We don't do it yet, but what did I say about Cl? It's a good what? Exactly, it's a good leaving group. So we don't make it leave yet. We're going to make it leave in the second one. So first things first, you get 1 mark for doing this. I like to put my delta positive in and your delta negative. Remember, Oxygen is anything that's electronegative is selfish. So what happens is the carbon's electrons are give it away to the oxygen. So that's why the arrow goes that way if you get confused. Now, because your carbon has basically given away all of its electrons to the oxygen, it becomes positive because it's less like got less electrons in it. So that's how you remember which way your arrow goes if you do forget when you do your mechanisms, because you've got your nucleophile, which is your NH2, because they're saying it here. It's giving its lone pairs to replenish the electrons it lost to give away to its oxygen. Does that sort of make sense about the reasoning why things go that way? So that's how you kind of remember which way things go. So you have CH2, CH3. That's done. Cool. So then the intermediate. So what's going to happen to my carbonyl group? Will it still be a double bond? What do I need to make sure I have on my oxygen? Yeah, single oxygen bond with a lone pair and a negative charge, okay? Then Cl hasn't gone yet, but it's going to go in a sec. CH3, CH2. Now, you have to put your NH there because that's where the lone pair was added to the carbon, right? So you have to do the NH and then CH3, CH2. Now, the N gave away its lone pair to the carbon to replenish it. So what charge does it have to have? Positive. So that's what you need to basically have the backbone of. So then we need to draw our thing. So it's an amide. So what do we need to do with the oxygen? Yeah, kick it back down. So we reform this. The Cl, again, is a good leaving group, so it will just go away. Now, you've got a H plus here. We don't like to have charges sticking out. So one of your H's has got to go to basically give away that charge. So you end up doing that. Okay, is everyone happy with that? Yeah. So then what do you actually make? So you have your C, you've got your double bond O, your Cl is going to kick off. You've got your CH3, CH2, you've got your N. Remember, we lost a H, so you have an NH, and then you have the rest of the schematic. Cool? So that's your amide. Now they want us to name it, okay? So again, we know it's an amide, so deal with what it actually like is. So is it primary, secondary, or tertiary? Secondary, right? So get your N out the way. Now we need to look at what's the shortest thing attached to the amine. What would you say it is? N what? Ethyl. So we've dealt with this side, that's done. Let's start with the other side. Now it's amide. So count, what would it be? Something amide. You've got how many, double check how many carbons you've actually got. Because the amide's naming the linkage, not the carbonyl group. Got a few things. 1, 2, 3 carbons. Propanamide. Does that make sense, everyone? How is N-E propanamide? Can you please do one for acid and hydride? Okay, so it's secondary. Yeah, I will do it now again. So primary, secondary, tertiary, it's secondary. So if it's secondary, we put N. We look at what is actually attached to the amine. That's why we have the N. So we look at the shortest chain. The shortest chain is that. So that's an ethyl group. So N-ethyl, okay? So we know it's something amide, okay? So we actually need to read the chain of what it's going to be. So we do 1 carbon, 2 carbon, and 3 carbons. So that becomes propanamide, okay? You may think it's ethanamide, but remember that amide is only naming this linkage, not the actual carbonyl group. So you have to include it in. Is that okay, Asif? I think it's AQA, but OCR can ask this. I think they do like a good, both of them like this sort of like acyl chloride stuff. Cool. Right, let's have a look at this one. So we've got student dissolves a few drops in propylamine in 1 centimeters cubed of water in a test tube. Give the equation for the reaction that occurs. Describe what is observed with the universal indicator. Okay, right. you've started off with water and it's adding universal indicator. So what color am I starting off with if it's started off with water? Green. Now, what color would amine be? You're only adding a few drops. So that's what they're saying to you. They've added a few drops. So what color would it be? Your amine will turn to what color? Is it, yeah, so we've got a few purples, but I would say blue. If they said like I've added in excess, then you say purple. But because they said a few drops, then I would go with blue. Okay. Yes. But then I've put in questions. It is AQA, but I'm putting these are the stuff that you should know, OCR, right? So you should know these things. Okay, right. Both of you need to know this. So I'm going to talk to you about this one. This is phenylamine, okay? How do you make phenylamine? From what I've gathered, both of you should know how to do acyl chloride based mechanisms. You may not get it with an amide, but you may likely get it with ammonia. So you'll likely, you know how you make an ammonium salt, right? With ammonia and like acyl chloride, that's more like an OCR type question. So it's basically, you know how I made the amide and how like the arrows go the same places, exactly the same, but you'll have a different, like you'll add ammonia, excess ammonia, for example, instead. Right, so we've got, yes, so we make SN and HCl. Okay, cool. So now the equation is like bog standard for the same sort of things. You need to figure out if you're reducing, you only care about hydrogens. So the H is the most like important thing because you care about that. You're going from NO2 basically to NH2, aren't you? So for every oxygen you have, you need to basically have a hydrogen it can go to. And then you need to have enough hydrogens to make that NH2. So how many H pluses or H2s do you need in total? Give me either or. So yeah, you need 6 H pluses because you've got two lots of O2, so that will make 2 lots of H2O, and then you need 2 lots of that. So then that makes, you need 6 H plus or 3 H2, okay? Yeah, so you've got O2, right? H2O. Every water has 1 oxygen, right? So that means you need 4 H pluses for that, or 2 H2s. Does that make sense there? How I did that and why? Yeah. Then you need enough H's for that. So you need either 1 more H2, so therefore you need 3 H2s, or 2 H pluses. So you either get 6 H pluses or 3 H2s. That's how you get that, okay? Cool, no worries. Right, so how do you actually write the equation? So the equation, you actually need to actually look at what they're asking you. They've told you they want it in reduction. So they're talking about H's. So that's why you say 6, okay? If they don't mention hydrogen, which we'll see later, that's when you can put the 3 H2s in, okay? So read the question properly. So you can't, do you want me to do it in state, or do you want me to draw it, or do you want me to draw it, do it in structural? It's up to you. You can do either or. Should I do it, write it? Okay, I'll write it. So you have C6H5NO2 plus 6H, right, gives you C6H5NH2 plus 2H2O. That's what you're expecting. If you draw it, just draw a nitrate, like nitrobenzene, and then a phenylamine. And then the explanation would be, we've got explain why aqueous solution is obtained in this reduction, even though phenylamine is insoluble in water. Basically, it's about if something is with 10 excess concentration of nitrobenzene, explain why the aqueous solution is obtained in this reduction, even though phenylamine is insoluble. Okay, so if you want to form an aqueous solution, what do you kind of need to have? You need ions, right? Yeah, you need ions, you need polarity. Okay, the only way that, well, what does ammonia what can ammonia become? An ion what? A positive ion what? NH4. So you remember how you can see it as an ammonium salt or ionic salt. So that is the reason why. So your phenylamine can present as an ionic salt, and that's why it can form an aqueous solution, even though it's insoluble in water. Do you want me to write that down? Yeah, okay. C6H5NH2 can present Is that all right? So just say that. Present as an ionic salt, so it will form an aqueous solution. You can even have like NH4 plus, whatever. That's fine. Cool. Right. I'm gonna do a synthetic route because we've already done an acyl chloride one. It's pretty much the same. Is that okay? So this one is an OCR one, so it's gonna be including everything. Oh, tell me when you're done. Is that all right? Aqueous solution is like a solution with like ions or like basically has water in it. So aqueous ions, things about stuff like that. Yeah, don't worry. It's fine. Right, I'm gonna move down just because of time. Okay, synthetic routes. So this is not amines, but it's going to include an amine, but you need to know it anyway. Right. So we've got what do we call the thing in the middle? What is it? Yeah, hydroxynitrile. Okay. So obviously, if we've got a nitrile, how do we go to an amine? What's our reagents? Yep. H2 and a nickel catalyst. That's done. Okay, so you've got hydroxynitrile wants to go to a carboxylic acid group. Okay, so how do we do that? What do we need to do? I would go for you can say any aqueous acid. Okay, so you can say HCl, you can say H2SO4. Yes, that's to make an amine, okay, from the nitrile group. So I would say HCl and then H2SO4. So any aqueous acid is fine, okay? Right. How do we go from a hydroxynitrile? What compound do you normally react? What do you need? Think about it. Because where's your OH come from? Where does your OH come from? What do you normally start off with? Yes, there you go, a ketone. So you need your carbonyl group for it to break. The CN comes through, and then obviously you add your ethanol, which is your H plus, and that's what forms the OH, doesn't it? So then you can just draw a basic ketone to do that. Everyone okay with that? Why it's a ketone and like why it's all everything that synthetic route. Cool. Well done. Right. Reaction three. So reaction three, if you basically got a CN and you want to make a carboxylic acid, so you need to just make it acidic, right? And it has to be aqueous because you've got your extra carbon, so you've done your carbon-carbon bond formation. You need to switch your N out for a carboxylic acid group. So that's why you need an aqueous acid to do that. Is that okay? Do they accept the alkane though? They're quite generous on that one. They said any sort of aqueous acid, any sort of haloalkane. Where does that extra? Because you've added an acid, right? It's got to be, that's why it's aqueous. So you're water essentially. Yeah? Yes. So use your extra oxygens and your extra H's, and that's what you basically add to make it a carboxylic acid. Okay, no worries. Cool. Right. Do you want me to skip this one? Do you want to move on to amino acids? Does everyone feel okay with amine so far? That's all you've pretty much got to know. Happy? Cool. Amino acids it is, because we've got 10 minutes, so I'm going to just do the ones that we'll do. Well, obviously, you're going to get access to the slides, so just do the questions we haven't done together and in your own minute for revision, okay? Right. Typically for amino acids, there's two sort of questions. They will, AQA, from what I've gathered, primarily want you to be able to draw them using the stuff in the data sheet and draw like dipeptide bonds and stuff, and also Zwitter ions. OCR is more synthetic, so they like you to do Zwitter ions, talk about chirality a lot, and also do synthesis with them. So that's what I would basically decipher. Obviously, the most important thing is you need to be able to draw them and also be able to understand the chirality between them. So what constitutes a chiral carbon? What do I need to have?
For the different functional groups.
Yeah, good. So we've got 4 different groups, well done. And then we'll go from there. So with amino acids, you need to know what a Zwitter ion is. So we've got an isoelectric point. You need to know that basically a Zwitter ion is basically an amino acid that basically becomes charged at its isoelectric point. Okay, so that, do you want me to write that down? Okay, and that is an isoelectric point. They could ask you what that is. That is basically what an amino acid becomes a Zwitter ion. Okay, so an amino acid so an isoelectric point could be a specific pH or anything like that. If they do ask you an isoelectric point, just say vice versa. It's when an amino acid becomes a Zwitter ion at a specific pH. So it's vice versa. Okay, so we need to draw a 3D diagram. Everyone stresses about 3D diagrams, just like with the wedges and the dashes. I'll kind of show you what it generally would look like. So let's draw cysteine and let's go from there. So generally you have your carbon in the middle. Your R group is normally straight at the top. Okay, so you have CH2, CSH, okay? Your least priority out of the whole carboxylic acid, you have COO, NH2, and H, right? Which one's the least priority? Yeah, so the least priority goes like that on the side. We don't really care about it. Then the other two get priority in terms of dashes, okay? To be honest, actually, I would draw it the other way, actually. Let's do a wedge and then go from there. So we could do a wedge, actually, put it the wrong way. And then we've got a dash, NH2, and then you see double bond O. Honestly, I wouldn't draw it this way. I would just do it this way. I think this is easier. So if this is easier for you to draw it like that, do it like this. Which I think is for everyone. Is everyone happy with the fact that this one's easier for them? Number 1. And what does it matter which? I think if you're gonna, I would say yes. It does matter which way your dashes go because they're just weird about it. But if you try and keep these two at a right angle, and then typically your wedges at the bottom, and this is basically what it generally should look like, you should be fine. So try and remember one off. Like, yeah. So least priority gets a wedge. Yes. AQA. You can draw it without. If I'm looking at the questions, you can draw it without. Okay. So even that, they said you can have it this way as well. So if it's a 3D diagram, you can still have it this way as well. Any or is fine. How do you decide between Q and NH to get to dash? I would just with which one with whatever which one gets like a dash whatever, it doesn't really matter. You can switch them, but typically straight line Q group, it's to do with priority. So if you look at like how it normally goes, you want to go like anti-clockwise in sort of priority. So COOH is the most sort of priority because it's got that double bond group. So you start off with your lowest priority and you want to go backwards. So that's how you kind of normally decide. That sulfur is more important than the nitrogen. So you can normally deal with it that way. And that's how I sort of think about it. But then you start going into enantiomers, and that's how you kind of draw enantiomers. That's why it's drawn that specific way. But I would get one like model answer on a flashcard and I would just learn it. That's probably the best way to do it. Okay, so they want to talk about alpha amino acid, lysine, reacts with excess dilute hydrochloric acid to form salt. We need to draw the salt basically formed, okay? So it's hydrochloric acid. So we are going to get what is going to react with what? The Cl is going to go where? With the Q group or the NH2? Yeah. So with the NH2, perfect. Because it's NH2 likes to go with chlorines generally. We never really like to see it with Q groups. Also, it says it's reacted in excess dilute acid. Okay. So what's going to happen to our NH2? It's going to become what? Positive and what? NH3 plus, there you go. So that's what you need to basically draw. So if we drew it, you have your H at the top, you have your Q group. We've got, let's get our ammonia out of the way. So we have H3N plus. I would just draw my Cl minus like that. Now, the issue is, do you see your R group? That's also got an ammonia in it. So you need to be able to deal with that. CH2, 4. So then you have NH3 plus Cl minus. Is everyone happy with that? So they tried to throw you off by also putting in the R group, deal with that as well. Okay? How? Because it's an ammonia, right? And it's in excess. So if you react it in excess, every single part of that ammonia has to basically interact with the HCl. So that's why. Is that okay? Cool. Right, let's do a synthetic route. Right, so we know obviously when you add a H plus, it's going to react with your amine. Okay, so get that out of the way because we've just covered that. So you have your C double bond OOH, H, CH2OH, and then you've got your NH3 plus because it's got a H plus added. Everyone okay with that part? Done. Okay, right. So then we've got an alcohol with H2SO4. If you add an alcohol, what is that going to react with to form? Perfect. Carboxylic acid to ester. Okay, so you're going to basically draw this out. So you've got H, CH2OH gives you H2N. And then you've got your carboxylic acid, like your carbonyl group. You keep your O and then add your methyl groups of your alcohol. So you've got 2 methyl groups and a CH. So we want to basically add that. So you've got CH3, CH3, then they've given you CH. That's what you basically want to add to get your ester. Now you've got excess, well, ethanol, we've basically got ethanol chloride. So what is that going to react with? Ethyl chloride make an ester and an amide. Yeah. It's going to want to go with your alcohol at the bottom. And then also you got your amide. So if you deal with, how would you actually draw that? You've got your H, you got your Q group normally. You've got your CH2. Remember your OH, that's going to basically want to form that ester bond. So the CL is going to basically jump off, and then you're going to make obviously your byproduct will be HCl because that H is gone, and then also your Cl's gone. And then you make your amide linkage. You have CH3 and then CO, and then we want NH, because again, we want to make 2 lots of HCl in replacement of that. Why does it go with the alcohol at the bottom? Because it's nucleophilic, okay? All your nucleophiles in this is obviously your OH and your NH2, okay? So that's why it's jumping on. To get rid of the Cl, they like to like add on to nucleophiles. Is that okay? Why does it not go at one? Because it's stuck basically in that carbonyl group. There's not enough power for it. So that's why it's going to hone in on actual nucleophiles with its lone pairs. There's no real lone pair. We have to break the bond with the carbonyl group for it to have a real lone pair. So that's why we wouldn't touch it. Whereas you've got 2 other available lone pairs. That's why it's honed in on that. I don't get the acyl chloride part. So why do we get the CH3 bond with the NH3? So the CH3 has come from here. You've got your CO that stays there. And then obviously your H from your O has gone and then gone with the Cl. Does that make sense? The CH, so you're taking the CH3s from your acyl chlorides. Okay. Okay, I'll draw it again. So you've got, if I rub this out, the pink is going to be from your acyl chloride. So CH3CO, O, okay? So the H has gone from your O and joined to made an HCl. And again here, CH3CO is your pink, and that's your NH to make. And then you've lost HCl. You've also lost HCl. Does that make sense? Thumbs up, thumbs down, let me know. Cool. Yes, exactly. That's why they said it in excess. Perfect. Cool. Right. So I'm just going to quickly talk about how to form a Zwitter ion, and then we'll call it a day. I know I've run over, but just like leave and it will be recorded anyway. So I'll put it on the YouTube later. So it said obviously phenylalanine. Look at your data booklet. It will have it in there. They've told you. So we've got phenylalanine. So then we've got this. Draw it out like a normal structure. CH2. You want CH. Now it's a Zwitter ion, right? So what I'm obviously gonna have NH3 plus. And then obviously the H from your carboxylic acid group has donated itself to the NH3. So you end up with an O minus. Is everyone okay with that? So you've covered all bases now. Cool. I'm gonna leave it there. I will send you guys the slides. Really well done. Hopefully Amines makes a bit more sense. How do you feel so guys so far? A bit better? Good. Right. I'll see you guys soon. Hopefully. I'm running an NMR session in an hour. I've got all your emails that you signed up with, so I'll email it to you. Okay? Because it will come up. Hopefully see you guys soon for the NMR session. I'll be running like webinars all weekend, so I'll put like the link in the chat for the NMR one if you want to join that. That's the NMR one. I've done an AQA one. If you look on my TikTok, because I've done an AQA one, I will do an OCR one tonight. Is that okay? Because I don't want to go down. But I really do think you're going to get like a lot of like amines and esters and stuff. Cool. Any more questions? I'll end the recording and then we can go through questions.